In our last example, we looked at a situation where the population of fish was growing at 10% per year. And we wrote out that multiplier as 100% plus the population percent growth. So in this case, it was 110% growth each year. So to find the amount of fish in a certain year, we would take the amount of fish from the previous year and multiply it by 110%. That's kind of a shortcut. You could multiply it by 10% and add it on, but the multiplier makes for a much easier and quicker process. And so we went through a few years and we came to the realization that if I wanted to find out the number of fish 50 years from now, this process would be pretty tedious, and maybe there's a shorter way to get there than multiplying by 1.150 times. All right, a little hint there in how we're going to do it. So let's take a look at this and let's think about what we did. Let's write it out in a little different way. All right, we know the p sub 0 was 1,000. All right, I'm going to use different colors here. So p sub 1, we took 1.1 times 1,000. And we got whatever we got. But you know what? I'm not going to write that number right now. Let's just kind of ignore the numbers for a second and think about the process. So for p sub 2, what did we do? Well, we took 1.1 and we multiplied that by whatever the population was for p1. All right, so what was the population for p1? Let's write that out. So p2 is 1.1 times, let's do a little times there, p1, which was 1.1 times 1,000. All right, so what's really the net result of that? Let's write that in black. So the net result of that is we took 1.1 times 1.1 times 1,000. So basically 1.1 squared times 1,000. All right, let's do a different color here for p3. Oh, let's see, how about aqua? So for p3, how do we do that? Well, we take 1.1 times p2. Okay, so how do we find p2? Oh, let me do p2 in red. Let's do p2 in red. 1.1 times p2. Okay, and I'm not going to write the number. I know we could figure out what the number is, but the object here is to see a pattern. Okay, so all of this is p2. So we're going to take 1.1 times 1.1 times 1.1 times 1,000. All right, so really what we're doing here is we're taking 1.1 times itself 3 times to get to this number. All right, another cool way of seeing what's happening is to make a table. Let's say we've got the year, and then we've got the population. All right, so in year 0, the population was 1,000. In year 1, the population was 1.1 times 1,000. In year 2, the population is 1.1 squared times 1,000. In year 3, the population is 1.1 cubed times 1,000. All right, I think you're seeing the pattern. I hope you're seeing the pattern. And it should make sense because what are we doing to get the next year? We're multiplying by 1.1. Then we have to take this times 1.1. Then we have to take this times 1.1. Did I make my arrow? Let's see. My arrow should be here, times another 1.1. So to get down to year 3, I got to multiply by 1.1 3 times. All right, so what if I want year 50? How am I going to find the population in year 50? Well, I'm going to have to take the initial population of 1,000, and I'm going to have to increase it by 110% 50 times. I'm going to have to multiply by 1.1 50 times. So you need to find on your calculator where your exponent button is. It's right here on this calculator. Every calculator is a little different, but so I'm going to do 1.1 to the 50th power equals times 1,000. That's a lot of fish. So I doubt the fish are going to follow this exponential growth pattern forever because of the capacity of the lake. And that's going to introduce a different type of growth that you'll learn about later, where the capacity of the lake or the petri dish or the earth inhibits the growth at some point. All right, so let's round this to 391. So maybe this isn't a great estimator for 50 years from now, but maybe 10 years from now, and still it would be a time saver if I wanted to figure out the population 10 years from now, or estimate the population 10 years from now, to do that, and as opposed to multiplying by 1.1 over and over again. All right, but here's the big step now. We want to generalize this. So n years from now, how will I find the population? Well, it's going to be 1.1 to the nth power times 1,000. So we could write that over here, and we could say the population n years from now is 1.1 to the nth power times 1,000 for this particular model. Now let's think about what is this 1.1 in general, because that could change depending on the situation, and what is this 1,000? So remember, the 1,000 was the initial population, and the 1.1 was the growth factor. Now, in the last video, I called the increase in population P, little p, and then I was commenting about how maybe that could be confusing with the capital P. So I'm going to change it to R for the rate. So I'm going to say R, let R equal, R percent, whatever that rate is of increase. How could I write that a little bit better? Let's just say there's an R percent increase or an R percent decrease. So then the growth factor, if R is positive, is going to be 100% plus R percent. Okay, if it's an R percent decrease, if the amount of fish was decreasing, then it would be 100% minus R percent, and that's going to be your growth factor. So that's where this 1.1 came in. So our general equation then, explicit, actually, hold on. I copied this from the other slide. This isn't the recursive formula now. What we're doing is we're doing the explicit formula. So the recursive formula is this bit right here. And the recursive formula basically only lets you take some population and find the population the next year. The explicit form is going to allow you to find the population in any year that you want. Okay, now the way I have this formula written down here, this is one you want to memorize, but understanding where it came from will definitely help you memorize it. This R would be expressed as a decimal. All right, like this 1.1. So the 10% would be 0.1. So it might be better to just say R percent increase or R over 100. We could even distinguish like capital R percent, and then let little r be the decimal approximation. We could do that. All right, let little r be the decimal for capital R percent. All right, so if capital R percent is 10%, then little r would be 0.1. All right, so we want that in decimal form. So this formula provides a lot of flexibility. Let's say that I've done some more research and now the population of fish is only increasing by 8%, and in a certain year that I'm starting this, now it's increasing by 8%. Say now there's 2,000 fish to start, and I want to determine the population 8 years from now. Well, with this explicit formula now, I can say the population 8 years from now is 1 plus little r, which is 8% as a decimal, to the nth power, so to the 8th power. And I just picked 8% in year 8 just out of nowhere. Those don't have to be the same. And I can just punch this into my calculator and get a quick answer. Very quick. 1.08 to the 8th power times 2,000. So under this model, in 8 years, we're going to have about 3,700 fish. All right, 3,702. All right, so that is the explicit formula for exponential growth. And remember, the key characteristic of exponential growth is percent increase or decrease. It has to be increasing or decreasing by the same percent, which will not be the same amount. All right, if you look over here, these are the numbers of the fish when we did them before. Let's see, the number before this for P1 was 110 or 1,100 fish and then 1,000 fish. So if you look here, this is increasing by 100 fish. This is increasing by 110 fish. This is increasing by, what is that, 121 fish. So this is not linear. If it was linear, these red numbers would be the same. This went up by 133 fish. Okay, so it's not linear growth because it's not increasing by the same amount, but it is increasing by the same percent. It's going up by 10% of the current population each subsequent year. And that's the key difference between linear and exponential growth.